when you have, let's say, some error in computing evaluation values of each of the nodes, when you combine them, the errors add up. They add up or multiply, depending on what you're doing. They don't reduce. Do you see what I'm saying? So if you want to get some quantity and you can actually directly measure that quantity, you're better off measuring it directly than measuring it indirectly and combining, using a big formula. Because whenever you do the big formula, then you have the way in which errors propagate through that formula. Okay? So it turns out that this you think is a good idea, it's not, and then I'll give you another one, which is maybe going deeper actually makes the agent do these traps, thus significantly improving the evaluation function accuracy. So the evaluation function itself is always saying, if win, take win, if loss, take loss, if draw, take draw, if not, do this evaluation function. How many of you remember from the last class? I don't have the slide right here, but there was, for the tic-tac-toe, the evaluation function said, if it is a definite win, evaluation is 1. If it's a definite, plus infinity, okay? And if it's a definite loss, evaluation is a minus infinity. If it's a definite draw, evaluation is 0. If it's neither of these three cases, then do the number of rows, columns, diagonals, open minus number of rows, columns, diagonals, open, diagonals. You see what I just did? So in essence, as we go down the search tree, if you actually find definite terminal nodes, evaluation function is going to take that into consideration, because in some sense the way you are doing the evaluation is you only apply it when you don't know it to be a probable win or loss. Which means, if your games are such that there are traps at shallow levels, the number of moves required to win a chess game is reasonably high, assuming a perfectly rational mind. Number of moves required to die ignoble death very fast. It's very few. You can actually die by making really bad moves very fast. Any interesting game, I would argue, actually has this property. They have shallow traps. You understand what I'm saying? You would not, if I said, this is a game and it will take 29 days and at the end of which only you will know who won or who lost. That becomes quite uninteresting, at least in case of board games. There should be ways in which people can lose very fast if they make bad moves. Okay, and then there are traps. Those traps are taken into account by the evaluation function. That's how the accuracy increases. So when I said you could make games which are pathological, such that when you go deeper, in fact, the evaluation function, the move accuracy reduces, that's because you can make very boring games that no humans play, and they don't have traps at shallow levels. You see what I'm saying? Because of which, that's why nobody plays them. So part of the reason for playing, whether you are a good player or bad player, is if you're a good player, you want to get the other person very fast. If you're a bad player, of course, you're trying to win, but you lose very fast anyway. Okay, so the temptation for playing the game is that it's actually, you can get done very fast if the other person is not playing. And in chess, certainly, this is true. It's actually not as true in Go, to the extent I understand Go. Okay, I understand chess very limited, at a very limited level, and Go even more limited than that. So everything I talk about board games, probably about the specific board games, is probably wrong, and you should read more about the games yourself. But in general, chess you can die ignoble deaths much faster than Go. Okay, and so traps are actually what make going deeper very important. Yes, sir.
Does that mean that code is more
What?
Does that mean that code is more
It's a very good way of looking at it. Probably yes. Probably yes. I mean, it's very hard for me to. How many of you play Go?
I've played it, but I don't play
What?
it. I've played it, but I don't play it very often.
Okay. So there's a problem with Go is apparently it's not at all popular in the US. Like at all popular in the US. And there are people, are there anybody from Asia, China, Korea? It's extremely popular there. And it's also becoming popular in UK. In fact, 10 years back when I was in UK once, in British Museum, on the side there was a huge Go tournament going on. You know, people just basically get together and play Go. So they were trying to get interested in that. And that's part of the reason why Dennis Hassabis, sitting in UK, was looking at Go. Of course, it's also known that Go is a hard game by AI standards, but nobody in US really cared. You know, we're not playing it anyway. Why do we need to do it? Okay. But so that's part of the issue. But I think it is indeed the case that part of the difficulty of Go is essentially there are no obvious trap states, which might make it more error. Eventually, all games are non-ergodic because you die, you lose, right? So, okay, so it's actually a very useful thing to understand. This particular analysis is like a second, maybe third order understanding of why you do something. And here, this is the business of being a hacker versus a computer scientist. You know, there are like tons of GitHub repositories that will do min-max search for it. Okay, and they won't tell you why actually it's supposed to be working. Why do you need to know? In fact, you know, it seems to me that the way civilization progresses is doing a large number of things that you have no clue why they work. And then you come to college where we are actually trying to see whether you know why you are doing what you're doing. Okay, many people don't actually understand this, and in fact, the guy who actually did this analysis is a guy whose name you will hear multiple times, called Julia Pearl. And even if you haven't heard Julia Pearl's name, Julia Pearl actually got a Turing Award 3 years back. Okay, he actually deserves lots of Turing Awards. This is not even the most important thing he did. You know, he actually did Bayes networks, which we'll talk about a lot. And he also is doing great work on causality, which is actually extremely important, and people not differentiating between causality and causation is half of the problem in the world right now in terms of AI's public misconceptions. Yes?
So he was the one that created min-max, or he was the one that
He showed, okay, that's actually a good question. Julia Pearl showed this analysis. Now, who did the min-max? Now, one of the nice things about, this whole area is, in fact, I don't have the, you know, there was a slide that I showed at the beginning of the game tree section with lots of, you know, elephants and stuff, you know, but it also has some people's faces. And these are all grades of computer science. Okay, we already know who did alpha beta pruning. I mean, at least who did the analysis of alpha beta pruning, Donald Knuth. Okay. Min-max search actually was originally done by the same guy whose name you use for the standard computer architecture, which is von Neumann. Okay, so 191 is created for min-max. He's a polymath and, you know, extremely, you know, smart guy, and probably way too hard to have around because he seems to know everything. Also. But anyway, so 191 did the min-max. Okay. Okay. Let's see. What I'm going to do now is make you think of games with nature, which is the beginnings of non-progression processes. So here is an interesting question. You learned, and in fact somebody was asking me this question here. You learned min-max search. And you're playing chess game, with your 2-year-old nephew. Okay, and so basically it's your turn to make a move and you're taking 15-20 minutes to basically do, fire up this min-max search and come up with the best move. People are all laughing at you. Why? You're doing the right thing, right? I mean, you're making sure that you'll win the game, and you're actually running min-max probably all the way to the leaf node, while the 2-year-old nephew is eating one of the pieces. Because nephew, 2-year-old, that's the point. They can't even tell the difference between a candy and a bomb. And you are using big ticket, like, big firepower against this particular quote-unquote enemy. Okay, opposition, right? Make sure that we won't lose. And we all laugh at you because we realize you have zero understanding of your opponent. You should be able to win against your 2-year-old opponent without actually doing much at all. If you wait, the opponent, 2-year-old nephew will also eat the king, and then you say, I win. And it will also help to have candied pieces. But here's a big point. Min-max makes an assumption. It makes an assumption of perfectly rational opponent who is out to get you. Perfect rationality for that opponent is not live and let live. It's let's get max. They want to basically win the game just as much as you want to win the game. Or equivalently, they want you to lose the game just as much as you want to win the game. In those cases, min-max is fine. If on the other hand, you're doing min-max with your 2-year-old nephew, then you have a problem of opponent modeling. Okay, now imagine you're actually playing the game against nature. Now it turns out nature doesn't quite play chess. Although during Harvey maybe nature would have played chess. Okay? I mean, at the risk, I think it's 2 weeks we can make Harvey plays. So, you put the chessboard outside, and then you make your move, nature your turn, and the board is done. And then, right? But mostly nature doesn't play chess. But in fact, your entire life is playing games against nature. Okay? Think of this very simple scenario where it's a grid world and you are in this start state and you want basically, one of the interesting things is for now, these are the good states. If you get there, you will get +1, like a big badge, +1, big reward. If you get here, you get -1 reward, which is kind of bad. Minus is generally bad, okay? And then you basically obviously want to make a beeline to the +1, right? There's no real game here. Well, there's a game in the following sense. You can only go up, down, left or right, which is fine, except when you want to go up, with 0.8 probability you actually go up. And 0.1 you go left, 0.1 you go right. Did you understand what I just said? This is just a simple case of a stochastic action. An action which doesn't have a deterministic outcome. You understood? Okay? So I make this move of going up and somebody else decides whether this is going to happen, this is going to happen, this is going to happen. I put these numbers 0.8, 0.1, 0.1. But that's basically, you can understand what those numbers are saying. You need to have a sense that nature is a very particular kind of an opponent. Nature is indifferent to your very existence. Okay, so in essence, whether you go this 80% of the time you go this way, 10% of the time you go this way, 10% of the time you go that way. That's what it will happen. Right? Okay, now you can view this sort of in between, interestingly enough. It can be seen as a generalization of single agent A-star search, where in A-star search actions have deterministic outcomes. Now all of a sudden you have stochastic outcomes of actions. Right? You can also view it as a kind of a generalization or a specialization, depending on the way you actually, we'll talk about in a minute, of min-max search. In one case, you are playing with an opponent who is out to get you. Another case, you're playing with an opponent who is just dialing it in. Just, okay, you made you, I'll make one. And then you spend enough time with this opponent and found that 80% of the time they make this move, but 1% of the time they do this move, 1% of the time, 10% of the time they make this move. You figure this out, then suddenly your opponent really is nature. They're not out to get you. Do you see what I'm saying? So this problem can be viewed both from min-max search point of view and from A-star search point of view. A-star search generalization, min-max search is sort of an interesting generalization, where you're changing the type of document. Okay? Now what we're going to do in doing MDPs is how to solve these kinds of problems. And so, not surprisingly, the insights that come in understanding Markov, these are basically, these kinds of problems go under the name of Markov decision processes. Pretty, impressive name. Okay? MDPs are chock full of insights because you can make connections between MDPs from the A-star search to one side, MDPs and min-max search to the other side. Okay? And so it's actually, it takes a while to wrap your head around it. And it's kind of a, it's something that, how many of you have heard of these kinds of problems already before? People who have taken this class last time should matter, but the rest, okay, good. So, most of you probably didn't hear about it, in your pretense, etc., because it's like a more interesting version, and it turns out that actually, it's a lot more general version. It's actually usable in many other scenarios. And when A-star search is too simplistic, and min-max search is too paranoid. It's not that it's too simplistic, it's too paranoid. Okay, so to understand that, I'm going to draw my tree here. Okay, so I am actually starting from start, which actually is apparently, this is 3 and 2. So I'm here, 3, 2. Wait. 3, 2, apparently I'm here. That's my state. Okay? I'm in 3, 2, and I can do these actions. Go right, go up, go down, go left. Okay? Now if I do go right, with the 0.8 probability, okay, so 3, 2 is here, remember, right? 3, 2 is this one. Okay? With 0.8 probability, when I go right, I will go to 4-2, which is this guy. In which case, I will get a nice happy reward of -1. With the 0.1 probability, I go to, with the 0.1 probability, so let's see, this is going right. So I go right. So with 10% probability I go this side, and 10% probability I go this side. Okay, so in this case I'm coming here. 3, 3. And if I go to 3, 3, I actually don't know what its value is. It turns out that one of the things I forgot to tell you is there's a little more information here, which is this is +1, this is -1. And then I also say, for every state you go through, you pay a state penalty or reward. And that is said to be -0.04. So if you don't know anything, so if you're going through a state, you basically, it's a cost of living, essentially. Every time you go through a state, you lose -0.04. When you get here, you will get +1, and again there's a little rectangle there that will show that once you get there, you reach nirvana. You no longer get to do any more actions. which basically means this is a non-ergodic domain, because this is a terminal state. Okay, this also is a terminal state of the different kind. This seems to be sort of, monotheistic theology of heaven and hell. Okay, this is the heaven, this is the hell, or vice versa, depending on what you're doing. Okay, so then basically this is +1, this is -1, everything else you get a minus 0.04 reward. It's called reward, but reward can be the positive or negative. It's the joy of living is plus 0.04. Cost of living minus 0.04. Depends on which kind of life you are having. You generally have great time just living, or it's just such a drag. Okay, it is important because that changes how you will actually decide your action. If it's such a drag, I'm sure you want to end it. Okay, and if it is a great time, you don't want to go to either heaven or hell. I'm having a great time here. Why do I want to go to heaven or hell? Because that's all end of our life. Okay, so keep that reward part in mind. So that's why when I got to 3.3, I got minus 0.04. I just put that as the value there. That's the immediate reward. Think of that as sort of an evaluation function. Okay, now notice of course that unlike this, the 4.2, once you came here, it's done. You can never go anywhere else. But this guy, you could have done more search underneath this. By doing it, you could have somehow changed its value from immediate reward to something that's more long-term value. I'm using this word value right now without defining it, sort of intuitively. We'll talk about defining it. Okay, so think of these as evaluation functions. This is -1, this is 0.04, this is also T1, you go up, that's also minus 0.04. And similarly, I have values here, similarly, I have values here, similarly, I have values here. Now, the interesting thing is deciding what action do I do now is just basically combining these values somehow, computing a value here, and then taking the direction that seems to have the best value. Right? Agreed? Seems just like with max search. The only question is, what am I supposed to do with these values? I seem to have this 0.8, 0.1, 0.1 here, and this -1, minus 0.04, minus 0.04 are the values. So what should be the backed-up value? Obviously, most of you would jump to the conclusion, done probabilities, all of us know that I'm supposed to multiply 0.8 by minus 0.1, minus 1, 0.1 by this, and 0.1 by this, add it up, that's the expected value. Do you live your life by expected values? No. Some of you are risk averse. You think if something can go wrong, it will certainly go wrong for me. So let me not drive. Let me not go to Grand Canyon. In fact, I had a friend, one of my son's friends, when they were in middle school, this kid clearly was risk averse. Didn't want to take any chances. It turns out that if you go to Grand Canyon, you might fall off. I don't know if you thought about this. And in fact, if you go to Grand Canyon and you go to visitor center, most of the writing there is not about how beautiful Grand Canyon is, but how many different ignoble deaths you can have in Grand Canyon. I'm not kidding. How many of you have gone to Grand Canyon? Am I right? If you go to the visitor center, they say, please take a shuttle bus, take a picture, go home. Because why? You die in the canyons, they have to lift you. It's a lot of work, and there are stupid people born in the middle. And they are the ones who are taking, pictures, by standing on the ledge. So anyway, my son's friend, basically, he was a risk-averse kid. He, didn't want to. They had a field trip to Grand Canyon. He went all the way to Grand Canyon, and then when he got off the bus, he didn't want to say in the beginning itself that I might fall off. I don't want to go to Grand Canyon. Instead, he went all the way to Grand Canyon. He got off the bus and said, "There's too much dust here. I don't want to go." It's a completely different reason. It's not that he was afraid of heights. He just didn't like dirty places, and there's just too much dirt. You know, somebody needs to first clean Grand Pen and then this is right? But anyway, that kind of a kid will say, yeah, you are saying this is 0.1, this is 0.1, but the bad things are the ones that will be happening to you. So I am going to assume that if whatever is the lowest value I will get is the value I will actually get. That is, I am, instead of some loser, I would say I am paranoid. That's one way of living life. And don't, smirk. Sometimes you live like this. And you know people who live like this. And then there are college kids. How else do you explain all the drunk driving on Friday nights? What part of drunk driving causes accidents don't people understand? Exactly. It's not going to happen to me. Most of the time, if there is anything good that is possible in this world, I will get it. Okay, I'm the chosen one. I'm chosen to be taken to the emergency room. That's mostly what I'm chosen for. That's another way of living. And if you do that, you take max. In this level. If on the other hand, you say, I want to basically be sort of quote-unquote rational and do the expected value, you actually do the expected value, which is 0.8 times this, 0.1 times this, and 0.1 times this. There are 3 backups. So, this level, it would either be min or max or expect. This level. Now, having come with some value here, what do you do here? There is no question. Everybody does the same thing. They maximize their utility. So you take max. So this layer, you'll always take max. This layer, you can either take min or max or expect. So you could either, if you are actually thinking that if you're playing this game against nature, and if you think nature is out to get you, you do actual min-max game against nature. If you're playing game against nature and you think you are the chosen one, you play max-max game against nature. Okay? And if you're playing game against nature and you realize that you are insignificant cosmic dust, and nature doesn't care about you, then you do expectation. Yes?
Of course, I assume there could be like something in between where we can compare
Yes. So in fact, one of the very interesting reasons I brought this up is in elementary courses, people will just act as if these are 3 completely different ideas. A-star search, A-star search. First exam is an A-star search. Second exam is on min-max. Third exam is an MDP. They should never meet, not even in your head. My point is they're all connected, essentially. And in fact, one of the issues you may want to think of, when you are providing a policy to somebody is their risk averseness. Do you see what I'm saying? In fact, again, how many of you, I don't know, do any of you have stock advisors? Like, no? Good, okay, we should talk later. I always wanted to have rich kids in my class. So, stock advisors are supposed to kind of figure out your risk averseness and then help you decide what your policy should be in terms of where you put your money. Okay? The most paranoid will basically put their money under their pillow. Actually, even that is bad, but still. Okay? And the most reckless will be putting the money in whatever is the craziest junk stock that came up, because they might actually just win big. Okay? So again, that's risk averseness aspect. Okay. So whatever this idea that I just showed you, where if you actually take expectation and backup, it turns out, first of all, you heard like a lot of things here. One is you know what is MDP. MDP is a problem. It's not a way to solve it, it's a problem. A particular way of solving MDP is this way. And this is actually an online solution because the deeper you go, hopefully, the better backed up values you get, just like in the other scenarios. Okay? Yes?
So, in the graph, if you say that you are going to go right, then why do we have branches who are going up and left?
What?
As well?
Where?
So if
No. I'm thinking, what are all the, no, again, remember this is, the entire point of AI is for the agent to figure out what do I do next. So the agent is in this particular cell and is asking herself, should I go left, right, up or down?
So that's 4 branches.
Yeah.
From 3 to.
Yeah.
So in the right branch itself, you have 3 more moves.
Yeah, because from there, again, there actually are 4 branches. It's just that I didn't show going left. Okay, because going left leaves you in the same state. Actually, that's another of those things that I didn't mention here, which basically, when you try to go in a direction, you go 0.8, with 0.8 probably you go in that direction, 0.1 you go in the other direction, the perpendicular direction, 0.1 and 0.1. And then one more special point is, if you are in a direction, if you try to go in a direction and there's a wall there, then you just stay in your. So in fact, a very, very, very interesting thing is, imagine you are here. Although I didn't show it here, imagine you are here. Can you imagine an agent who tries to go this direction rather than up or down other side?
Roomba.
What?
Roomba.
Roomba, but people. Have you seen people on the Grand Canyon trails, like me for example? The point is, if you make this action, you die. -1 basically means you fall down. Okay? If you go this, you don't die, but there's still a chance that you die. Right? Because when you're going up, 80% go up, 10% go this side. If you go this way, you still go 80% this way, 10% this way. If you don't want to die, what's the best way to make progress? Hug the wall. That's where the canyons have walls. You see me hugging the wall when you go on the trail. Because I'm trying to go through the wall. And then one of you slowly push me one side. That's how I make my progress. And in fact, if the agent tries to go this direction, 80% of the time it just stays there, which is good, not dead. 10% of the time it goes up. Again good, not dead. 10% of the time goes this way. Again good, not dead. Do you see what I'm saying? Again, as I said, MDPs and stochastic actions just open up the world for you. And you understand the crazy thing.